So here's something kind of wonderful to think about as you're lying there, getting comfortable, letting the day wind down. Right now, inside your skull, about 86 billion neurons are doing their thing. They're firing, or not firing, passing tiny electrochemical signals to each other across gaps so small you'd need an electron microscope to see them. And somehow, out of all that quiet chatter, all those billions of little on-off decisions happening in parallel, you get this. Consciousness, memory, the ability to recognize your mother's face in a crowd, or to feel a little sad when a song catches you off guard, or to understand the words I'm saying right now and turn them into meaning. Nobody told your neurons how to do that. They just figured it out. Over time, through experience, through repetition, through something we're still honestly trying to fully understand. And here's the thing. For a very long time, centuries really, people looked at the human brain and thought, what if we could build something that works like that? Not a brain, exactly, but something inspired by it. Something that could learn, not because someone programmed every rule into it, but because it was exposed to the world and gradually on its own started to pick up patterns, started to get it. That idea, that dream really, is where neural networks come from. And tonight, we're going to trace the whole story. How people went from barely understanding what a neuron even was to building systems that can translate languages, drive cars, generate images, and beat world champions at games that were supposed to be too complex for any machine to master. We'll go slowly. We'll take detours. If you fall asleep somewhere in the middle, that's completely fine. That's sort of the point. But if you stay with me, I think you'll find this is one of the most fascinating stories in the history of engineering, because it's not just a story about computers. It's a story about people trying to understand thinking itself. Let's start way back, before computers, before electricity even. Let's start with the neuron. For most of human history, nobody knew what the brain was actually made of. The ancient Egyptians thought the heart was the seat of intelligence. When they mummified someone, they'd carefully preserve the heart, but basically scoop the brain out through the nose and throw it away. The Greeks were a little closer. Hippocrates, around 400 BC, argued that the brain was the organ of sensation and thought, which was pretty bold for the time, but even he had no idea what was going on inside it at a cellular level. How could he? There were no microscopes. Fast forward a couple thousand years to the late 1800s. This is when a Spanish scientist named Santiago Ramón y Cajal enters the picture, and he's one of those figures in science who deserves to be way more famous than he is. Cajal was born in 1852 in a small town in Navarre, in northern Spain. His father was a surgeon who wanted young Santiago to follow him into medicine, but the kid was more interested in drawing and painting. He was actually a talented artist, and that detail matters because it's precisely that artistic skill that would later change everything. Cajal studied medicine as his father wished, but he became obsessed with microscopy. He spent hours hunched over a microscope, staring at thin slices of biological tissue, and then he'd draw what he saw with extraordinary precision and beauty. And what he turned his attention to in the 1880s was the nervous system. At the time, there was a huge debate in biology. One camp believed the nervous system was basically one continuous network, like a big web of connected fibers, all fused together. This was called reticular theory. The other camp thought the nervous system was made up of individual discrete cells, that were close to each other, but not actually physically connected. Kajal, through years of painstaking microscopy and those gorgeous, meticulous drawings, proved that the second view was right. The brain was made of individual cells, neurons, that communicated across tiny gaps. Those gaps would later be called synapses. This was huge. Kajal shared the Nobel Prize in Physiology or Medicine in 1906 for this work, and his insight gave us the basic picture of how the brain is organized. You have neurons. Each neuron has a cell body, and branching out from it are these tree-like extensions called dendrites that receive signals from other neurons. Then there's a long fiber, called an axon, that carries signals away from the cell body and passes them on to the next neuron. The signal jumps across the synapse, that tiny gap, using chemical messengers called neurotransmitters. And the key insight, the one that matters for our story, is this. A neuron receives inputs from many other neurons through its dendrites. Some of those inputs are excitatory. They encourage the neuron to fire. Some are inhibitory. They discourage it. The neuron essentially adds all of this up, and if the total excitation crosses some threshold, the neuron fires and sends its own signal down its axon to the next set of neurons. If the total doesn't cross the threshold, the neuron stays quiet. Think about what that means. Each neuron is making a tiny decision. Yes or no. Fire or don't fire, based on the combined weight of all the signals coming in. It's not exactly like a computer switch. Biology is messier and more nuanced than that. But there's something deeply computational about it. And that resemblance is what caught people's attention. Now let's jump forward to 1943. The world is at war. Alan Turing is working on code breaking at Bletchley Park. The first electronic computers are being built, enormous, room-filling machines made of vacuum tubes designed to calculate artillery trajectories and crack encrypted messages. And in this environment, two men published a paper that would plant the very first seed of neural networks as we know them. Their names were Warren McCulloch and Walter Pitts. McCulloch was a neurophysiologist, a medical doctor and philosopher who was deeply interested in how the brain produces thought. Pitts was remarkable. He was essentially self-taught, a prodigy from a troubled background in Detroit. The story goes that as a teenager, Pitts stumbled across Bertrand Russell's Principia Mathematica in a library, one of the most dense, abstract works of mathematical logic ever written, and found errors in it. He wrote to Russell about them. Russell was so impressed that he invited the kid to come study at Cambridge. Pitts couldn't afford to go, but he eventually ended up at the University of Chicago, where he met McCulloch. Together, in 1943, they published a paper called A Logical Calculus of the Ideas Immanent in Nervous Activity. The title is a mouthful, but the idea was elegant. They proposed a simplified mathematical model of a neuron. In their model, a neuron receives a bunch of binary inputs, ones and zeros, on or off, and each input has a weight. The neuron multiplies each input by its weight, adds everything up, and if the total exceeds a certain threshold, the neuron outputs a 1. If not, it outputs a 0. Now, this is a massive simplification of what a real biological neuron does. Real neurons deal with continuous signals, complex timing, chemical gradients, all sorts of messy biological reality. McCulloch and Pitts knew that. They weren't trying to perfectly replicate biology. They were asking a more fundamental question. If you had a network of these simple, idealized neurons, what could it compute? and the answer turned out to be surprisingly powerful. They showed that a network of these model neurons could, in principle, compute anything that a Turing machine could compute. In other words, these little threshold units, wired together in the right way, were capable of universal computation. That's a wild result. Think about it. Take the simplest possible model of a brain cell, something that just adds up weighted inputs and checks if they cross a threshold, and wire enough of them together, and you can compute anything. Anything a computer can do, in theory, a network of these things can do too. But here's the catch, and it's an important one. McCulloch and Pitts didn't say anything about how the network should learn. In their model, the weights and the connections were fixed. Someone, a designer, a programmer, would have to figure out the right weights and wire everything up by hand. The network didn't adapt. It didn't learn from experience. It was a computational architecture, not a learning system. And the whole dream, remember, was to build something that could learn. So the McCulloch-Pitts neuron was the foundation, the proof that this kind of approach could work in principle. But the real breakthrough, the one that made people genuinely excited, came a few years later from a psychologist named Frank Rosenblatt. Rosenblatt was born in 1928 in New Rochelle, New York. He went to Cornell, got his PhD in psychology, and ended up working at the Cornell Aeronautical Laboratory in Buffalo. He was interested in perception, specifically how the brain recognizes patterns. How does a child learn to tell the difference between a cat and a dog? Not by being given a list of rules. Cats have pointed ears, dogs have floppy ears, because that doesn't really work. There are cats with floppy ears and dogs with pointed ears. Instead, a child just sees a lot of cats and a lot of dogs, and somehow, the brain figures it out. Rosenblatt wanted to build a machine that could do the same thing. In 1958, he unveiled the perceptron, and the perceptron was, in some ways, very similar to the McCulloch-Pitts neuron. It took a set of inputs, multiplied each one by a weight, summed them up, and checked if the result crossed a threshold. If it did, the output was 1. If not, 0. Simple enough. But here's what made the perceptron different, and here's what made it genuinely revolutionary. It could learn. Rosenblatt designed a learning rule for the perceptron. You'd show it an input, say, a simple image, and tell it what the correct output should be. If the perceptron got the answer right, you'd leave the weights alone. If it got the answer wrong, you'd adjust the weights a little bit, nudging them in the direction that would have produced the correct answer. Then you'd show it another input, and another, and another, and each time, the weights would get tweaked slightly. Over many examples, the perceptron would gradually converge on a set of weights that let it classify the inputs correctly. This is worth pausing on because it's the core idea that underlies everything in neural networks, even today. The machine isn't programmed with rules. Instead, it's given examples and a way to adjust itself when it's wrong. Learning, in this framework, is just the slow, iterative process of adjusting weights until the errors go away. It's remarkably similar, at least in spirit, to what we think happens in the brain, where the strength of synaptic connections between neurons changes based on experience. Neurons that fire together wire together, as the saying goes. Rosenblatt built a physical perceptron machine, the Mark I perceptron, at the Cornell Aeronautical Laboratory. It was a bizarre-looking contraption. It had a grid of 400 photocells, basically a very crude camera, that could detect light and dark in a 20 by 20 array. These photocells were connected to a layer of artificial neurons through a tangle of wires, and the connection weights were implemented using motorized potentiometers, little adjustable resistors controlled by electric motors. When the machine learned, the motors would physically turn the potentiometers to change the weights. You could hear it learning. Little motors whirring away as the machine adjusted itself. The Navy funded the project, and in 1958, the New York Times ran a story about it with a headline that was, let's say, optimistic. The article suggested that the perceptron was the embryo of a computer that would eventually be able to walk, talk, see, write, reproduce itself, and be conscious of its existence. Rosenblatt himself was enthusiastic, but more measured than the press coverage suggested. Still, the excitement was real. Here was a machine that could actually learn to distinguish simple patterns, and it worked. You could show it simple shapes, letters, and it would learn to categorize them. But not everyone was impressed. And the most prominent skeptic was someone Rosenblatt knew personally, a man named Marvin Minsky, who had actually been Rosenblatt's classmate at the Bronx High School of Science back in the 1940s. Minsky had gone on to become one of the founders of the field of artificial intelligence at MIT, and he had a very different vision of how to build intelligent machines. Minsky believed in what's sometimes called good old-fashioned AI, the idea that intelligence comes from symbolic reasoning, from manipulating logical rules and representations, not from mimicking neurons. And he thought the perceptron was being dramatically oversold. In 1969, Minsky and a colleague named Seymour Papert published a book simply called Perceptrons. And this book was devastating. What Minsky and Papert showed, with rigorous mathematical proofs, was that a single-layer perceptron, the kind Rosenblatt had built, had fundamental limitations. There were simple problems it simply could not solve. The most famous example was something called the XOR problem, and it's worth understanding because it illustrates a really important concept. XOR stands for exclusive OR. It's a logical operation. Imagine you have two inputs, each of which can be 0 or 1. XOR outputs a 1 if exactly one of the inputs is 1, but not both. So, 0 and 0 gives 0. 1 and 0 gives 1. 0 and 1 gives 1. But 1 and 1 gives 0. It's like asking, are these two things different? Simple enough for you and me to understand. But Minsky and Papert proved that a single-layer perceptron literally cannot learn this function. No matter how you adjust the weights, you can't get it to correctly classify all four cases. The reason has to do with geometry. A single-layer perceptron can only draw a straight line through its input space to separate the categories, and the XOR problem requires a boundary that isn't a straight line. It needs a curve, or two lines, or something more complex. Now here's what's important. Minsky and Papert knew, and even acknowledged in their book, that multi-layer networks with additional layers of neurons between the input and the output, could in principle solve the XOR problem and many others. The issue was that nobody knew how to train them. Rosenblatt's learning rule worked beautifully for a single layer, but when you added more layers, there was no known method for figuring out how to adjust all those internal weights. The learning signal, the information about what went wrong, got lost in the middle layers. How do you tell a neuron buried deep inside the network that it contributed to an error at the output? Nobody had a good answer. And so, the effect of Minsky and Papert's book was chilling. Funding dried up. Researchers moved on to other approaches. The perceptron, and neural networks more broadly, fell into what's sometimes called the first AI winter, a period of reduced funding, reduced interest, and a general sense that this whole approach was a dead end. Rosenblatt himself died tragically in a boating accident on Chesapeake Bay in 1971 on his 43rd birthday. He never saw what would come next. But the story doesn't end there. Because even during the quiet years, a handful of researchers kept working on the problem. They kept asking, what if we could train those deeper networks? What if we could find a way to send the learning signal backward through multiple layers, adjusting every weight along the way? And the answer to that question, when it finally came together, would change everything. It would change everything about how we think about machine learning, about artificial intelligence, about what computers can do. And the beautiful thing is, the core idea isn't even that complicated once you see it. So, let's talk about what happened during those quiet years. Because the AI winter wasn't total silence. It wasn't like every single person on Earth stopped thinking about neural networks the moment Minsky and Papert's book hit the shelves. Science doesn't work that way. What happens is that the mainstream moves on. The big funding agencies redirect their money. The prestigious journals stop accepting your papers, and the graduate students get advised to work on something else if they want a career. But there are always a few stubborn people who keep going. People who look at the evidence and think, no, there's something here. I can feel it, and I'm not ready to give up yet. One of those people was a Finnish computer scientist named Seppo Linnanmaa. In 1970, just a year after Minsky and Papert's book came out, Linnanmaa published his master's thesis at the University of Helsinki. And in that thesis, he described a general method for automatically computing derivatives through a chain of nested mathematical functions. Now that might sound abstract, and it is abstract, but stay with me because this is one of those foundational ideas that everything else builds on. What Linnanmaa described was essentially the algorithm we now call reverse mode automatic differentiation. And if that term means nothing to you right now, don't worry. We're going to unpack it slowly, because it turns out this is the mathematical heart of how neural networks learn. Let's start with something simple. You remember how a neuron in a network takes inputs, multiplies them by weights, adds them up, and checks if the result crosses a threshold? And how learning means adjusting those weights so the network gives better answers. Well, the key question is, when the network gets something wrong, how do you know which weights to change, and by how much? Think about it this way. Imagine you're trying to tune a guitar, but you're wearing thick gloves, and the guitar has 100 strings, and you can only hear the final chord. You can't isolate individual strings. You strum, and the chord sounds wrong. You know something needs adjusting, but which string? And should you tighten it or loosen it? And by how much? That's essentially the problem of training a multi-layer neural network. The output is wrong, but the error could be caused by any of hundreds or thousands of weights deep inside the network, and you need to figure out each one's individual contribution to that error. Here's where calculus comes in, and I promise this won't hurt. The basic idea is something called a derivative, which is just a way of asking, if I nudge this one thing a tiny bit, how much does that other thing change? If I tighten this guitar string by a tiny amount, how much does the overall chord change? That's a derivative. It tells you the sensitivity of one quantity to changes in another. And if you can compute the derivative of the network's error with respect to every single weight in the network, then you know exactly how to adjust each weight to reduce the error. You nudge each weight in the direction that makes the error smaller, by an amount proportional to how sensitive the error is to that weight. Weights that have a big effect on the error get adjusted a lot. Weights that barely matter get adjusted just a little. And you do this over and over, with example after example, and the network gradually gets better. This process of following the derivatives downhill, reducing the error step by step, is called gradient descent, and the word gradient just means a collection of all those derivatives, one for each weight. It's like a big arrow pointing in the direction of steepest improvement. You compute the gradient, you take a small step in that direction, and you repeat. It's remarkably similar to the way water flows downhill. Water doesn't know calculus, but it always finds the path of steepest descent. Gradient descent does the same thing, but in a space with potentially millions of dimensions, one dimension for each weight in the network. Now, gradient descent as a concept had been around for a long time. Mathematicians had been using it since at least the 1840s, when Augustin Louis Cauchy described the method. The hard part wasn't the concept of following the gradient. The hard part was computing the gradient efficiently in a network with multiple layers. And that's where Linane Ma's insight comes in. Because in a multi-layer network, the output depends on the weights in the last layer, which depend on the outputs of the previous layer, which depend on the weights in that layer, which depend on the outputs of the layer before that, and so on, all the way back to the inputs. It's a chain of dependencies. And calculus has a rule for exactly this situation. It's called the chain rule. If you know how A affects B and how B affects C, then you can figure out how A affects C by multiplying those two effects together. And you can extend this through as many links as you want. How does A affect D? Well, A affects B, B affects C, C affects D. Multiply all three sensitivities together. What Linane Ma showed was that you could compute all of these chain derivatives efficiently by working backward. You start at the output, where you know the error, and you propagate information about that error backward through the network, layer by layer, computing the derivative for each weight as you go. The key insight is that by going backward, you can reuse intermediate calculations, which makes the whole process dramatically faster than computing each derivative separately. Instead of the computation time growing with the square of the number of weights, or worse, it grows roughly linearly. That's the difference between something that's practical and something that would take longer than the age of the universe. But here's the thing. Linane Ma's thesis was about automatic differentiation in general. He wasn't specifically thinking about neural networks. The connection between this mathematical technique and the problem of training multi-layer networks took time to crystallize, and it happened in several places, with several people, in a way that makes it genuinely hard to assign credit to any single individual. One important thread runs through Paul Werbos, an American researcher who was working on his PhD at Harvard in the early 1970s. Werbos was interested in a big, ambitious question. He wanted to build mathematical models of complex systems, like economies or ecosystems, and he realized that the chain rule applied backward through a computational graph was the key to making these models learnable. In his 1974 PhD thesis, Werbos described what he called back-propagation, the idea of propagating error signals backward through a network to compute gradients. He explicitly connected this to neural networks and argued that it could be used to train multi-layer systems. But Werbos was a graduate student, working somewhat outside the mainstream. His thesis was dense and difficult, and the AI community had largely moved on from neural networks. His work didn't get the attention it deserved. Not yet. Meanwhile, across the Atlantic, similar ideas were bubbling up independently. In 1986, and this is the date most people associate with the back-propagation revolution, David Rumelhart, Geoffrey Hinton, and Ronald Williams published a paper in the journal Nature titled Learning Representations by Back-Propagating Errors. And this paper changed the game. not because the core mathematics was entirely new. Werbos and others had been there before, but because Rumelhart, Hinton, and Williams presented the idea clearly, demonstrated it convincingly on real problems, and published it in one of the most prestigious scientific journals in the world, at a moment when the field was ready to listen again. Let me tell you a little about these three, because they matter. David Rumelhart was a cognitive psychologist at UC San Diego, deeply interested in how the human mind processes information. He wasn't a pure mathematician or a computer scientist. He came at this from the perspective of someone trying to understand human cognition, and he believed that networks of simple processing units were the right framework. Geoffrey Hinton, who would go on to become one of the most influential figures in all of artificial intelligence, sometimes called a godfather of deep learning, was a British-Canadian cognitive psychologist and computer scientist who had been thinking about neural networks since the 1970s, even when it was deeply unfashionable. Hinton had a stubborn conviction that the brain-inspired approach was right, and he kept working on it through the entire AI winter, at a time when doing so was genuinely bad for your career. Ronald Williams was a computer scientist at Northeastern University who contributed crucial mathematical insights to the work. What their 1986 paper showed was this: take a network with an input layer, one or more hidden layers, and an output layer. Present it with a training example. Let the signals flow forward through the network to produce an output. Compare that output to the correct answer and compute an error. Then propagate that error backward through the network, using the chain rule, to compute the gradient, the derivative of the error with respect to every weight in the network. Then adjust every weight a small amount in the direction that reduces the error. Repeat with the next training example. And the next. And the next. But there was one more crucial ingredient that made this work, and it's something we haven't talked about yet. Remember how McCulloch and Pitt's original neuron was binary? It was either on or off, firing or not firing, and Rosenblatt's perceptron used a similar hard threshold? Well, here's the problem with that for backpropagation. The chain rule requires you to compute derivatives, and a hard threshold function, something that jumps suddenly from 0 to 1, doesn't have a useful derivative. At the jump point, the derivative is technically infinite, and everywhere else it's 0. You can't do gradient descent on a cliff face. There's no gentle slope to follow. So what Rumelhart, Hinton, and Williams used instead was a smooth activation function. Specifically, the sigmoid function, which looks like a gentle S-curve. Instead of snapping from 0 to 1, it transitions smoothly. A neuron with a sigmoid activation gives you a number between 0 and 1, and the function has a nice, well-behaved derivative everywhere. This means you can compute exactly how a small change in the neuron's input would change its output, and chain those computations together across layers. The smoothness is what makes the calculus work. It's what gives gradient descent a slope to follow. And this is one of those moments where a seemingly small technical choice, swapping a hard threshold for a smooth curve, unlocks an entire universe of capability. Without smooth activation functions, backpropagation doesn't work. With them, you can train networks with 2 layers, 3 layers, 10 layers, in principle, as many as you want. Each layer can learn its own internal representation of the data, its own way of carving up the problem, and the layers build on each other to capture increasingly abstract patterns. The 1986 paper demonstrated this on several problems, including some that single-layer perceptrons couldn't touch, and the reaction from the research community was electric. Suddenly, neural networks were interesting again. Funding started flowing back. Graduate students started choosing neural network research for their dissertations. The AI winter, at least for neural networks, began to thaw. But let's not get ahead of ourselves, because the story of what happened next is more complicated than a simple triumph. Back-propagation worked, yes. It was a genuine breakthrough. But it came with its own set of problems, subtle, frustrating problems that would take decades to fully solve. And one of the first things researchers discovered, as they tried to build deeper and deeper networks, was something called the vanishing gradient problem. It's a beautiful example of how a solution to one problem can create an entirely new problem that's almost as bad. And to understand it, you need to think about what happens when you multiply a bunch of small numbers together. That's really the heart of it. Imagine you have a chain of numbers, and each one is, say, 0.25. Not tiny, right? A quarter is a perfectly reasonable number on its own, but multiply two of them together, and you get 0.0625. Multiply 3 and you're down to about 0.016. 4 of them, 0.004. You can see where this is going. By the time you've multiplied 10 of those together, you're at something like 0.000001. Practically zero. And that's exactly what happens inside a deep neural network when you try to send error signals backward through many layers using backpropagation. Here's why. Remember that the sigmoid function, that smooth, S-shaped curve, has a derivative, and that derivative tells you how sensitive the output is to changes in the input. The maximum value of the sigmoid's derivative is 0.25. It happens right at the midpoint of the curve, where the function is steepest. Everywhere else, the derivative is smaller. So when you're backpropagating through a layer, you're multiplying by this derivative, and it's always a number between 0 and 0.25. Now chain that across layers. Each layer multiplies the gradient by its own sigmoid derivative. After 5 layers, your gradient has been multiplied by something like 0.25 to the 5th power. After 10 layers, it's 0.25 to the 10th. The signal that's supposed to tell the early layers how to adjust their weights has essentially evaporated. It's not that it's exactly 0, it's just so astronomically small that it's useless for learning. The early layers in the network barely change at all during training. They're effectively frozen, stuck with whatever random weights they started with. And this is deeply frustrating, because those early layers are arguably the most important ones. They're the layers that see the raw data first. They're supposed to learn the basic features, edges in an image, phonemes in speech, simple patterns in text. If they can't learn, then the later layers have nothing meaningful to build on. It's like trying to construct a building where the foundation is made of whatever random rubble happened to be lying around, and you're only allowed to carefully engineer the roof. You can make the roof beautiful, but the whole thing is still going to be shaky. Researchers in the late 1980s and early 90s hit this wall hard. They'd get excited about the theoretical power of deep networks with many layers, and then discover that in practice, they could only reliably train networks with 2 or 3 layers. Maybe 4, if they were lucky, and the problem was forgiving. Anything deeper, and the early layers just wouldn't learn. The gradients vanished before they got there, and this wasn't a subtle effect you needed instruments to detect. You could watch it happen. You'd plot the magnitude of the weight updates at each layer during training, and the first layer's updates would be thousands or millions of times smaller than the last layers. The network was learning, technically, but only at the end. The front was dead. Now, there's actually a mirror image of this problem that's worth mentioning, called the exploding gradient problem. If instead of all those multiplicative factors being less than 1, some of them are greater than 1, then the chain of multiplications doesn't shrink to zero, it blows up to infinity. Your gradients become enormous, the weight updates are wildly too large, and the network's weights careen off into nonsensical values. The training process becomes completely unstable, so you're caught between two failure modes: gradients that are too small and gradients that are too large, and finding the sweet spot in between, especially for deep networks, turned out to be incredibly difficult with the tools available in the early 1990s. This is one of the reasons that neural networks fell out of favor again. Not completely. There were always true believers working on them. But the mainstream of machine learning research shifted toward other methods. Support vector machines became very popular in the 90s. They had elegant mathematical foundations. They worked well on many practical problems, and they didn't suffer from these maddening training instabilities. Decision trees, random forests, kernel methods. There were plenty of alternatives that seemed more reliable, more predictable, more tractable. Neural networks started to feel like a beautiful idea that just didn't scale. You could do cute demos with them, sure, but could you really build serious systems? A lot of smart people thought the answer was no. And here's where we need to talk about a few people who disagreed, because the story of how neural networks came back so dramatically that they now dominate artificial intelligence, is really the story of a handful of stubborn researchers who kept working on the problem when almost everyone else had moved on. And the most important of them, the one whose name comes up again and again, is Geoffrey Hinton. We've already met Hinton as one of the authors of that landmark 1986 Back-Propagation paper. But his role in the story is much bigger than that. Hinton is a British-Canadian computer scientist who spent decades at the University of Toronto, and he is, more than any other single person, responsible for the deep learning revolution. But in the 1990s and early 2000s, being a neural network researcher was not a glamorous position. Hinton has talked about this openly, how hard it was to get funding, how reviewers would reject papers simply because they were about neural networks, how the field was considered something of a backwater. He's described going to conferences and feeling like people looked at neural network researchers the way you might look at someone who still believed in alchemy. There was this pervasive sense that the approach had been tried, it had fundamental limitations, and serious researchers should move on to more promising techniques. But Hinton kept going, and he wasn't alone. Yann LeCun, a French computer scientist who'd studied under Hinton's collaborators, was doing remarkable work at Bell Labs and later at New York University. LeCun had developed convolutional neural networks in the late 80s and early 90s, a specialized architecture designed for processing images, inspired by how the visual cortex works, and he'd actually gotten them to work on practical problems. A T&T used his system to read handwritten checks, processing millions of checks per day. It was a real, deployed, commercial neural network system, and it worked beautifully. But even that success didn't convince the broader research community. People saw it as a special case, a clever trick for one particular problem, not evidence that neural networks were a general-purpose tool. And then there was Yoshua Bengio, a Canadian researcher at the University of Montreal, who was doing deep theoretical work on why deep networks were hard to train and how they might be fixed. These three, Hinton, LeCun, and Bengio, are sometimes called the godfathers of deep learning, and in 2018 they shared the Turing Award, which is essentially the Nobel Prize of computer science, for their work. But in the late 90s, they were more like a small band of holdouts, keeping the flame alive while the rest of the field looked elsewhere. So what changed? What brought neural networks back from the dead a second time? It wasn't one single thing. It was a convergence of several developments that all came together in the span of about a decade. And the first piece of the puzzle was figuring out how to actually train deep networks, how to solve, or at least work around, the vanishing gradient problem. One of the key breakthroughs came from Hinton himself in 2006. He published a paper showing that you could train deep networks using a clever two-phase approach. First, you'd pre-train each layer of the network one at a time, using an unsupervised method, meaning you didn't need labeled data. Each layer would learn to model the statistical structure of its inputs, essentially learning useful features on its own. Then, once all the layers had been pre-trained this way, you'd fine-tune the whole network using backpropagation and labeled data in the normal supervised way. The pre-training gave the weights a much better starting point, so when backpropagation kicked in, the gradients didn't have as far to travel, metaphorically speaking. The network was already in a reasonable neighborhood of a good solution, and backpropagation just needed to make local adjustments rather than trying to move the weights across vast distances from their random starting points. This was a big deal. It showed that deep networks with 5, 6, 7 or more layers, could actually be trained to work well on real problems. And it reignited interest in the field almost overnight. But the pre-training approach, while important historically, turned out to be a stepping stone rather than the final answer, because other researchers were finding simpler solutions to the vanishing gradient problem that didn't require the elaborate pre-training step. One of the most important of these simpler solutions was almost embarrassingly straightforward. It was just a different activation function. Remember how the sigmoid's derivative maxes out at 0.25, and that's what causes the gradients to shrink? Well, what if you used a different function whose derivative didn't have that problem? In 2010 and 2011, researchers started experimenting seriously with something called the rectified linear unit, or ReLU. And I love this one because of how simple it is. The ReLU function is just, if the input is negative, output 0. If the input is positive, output the input unchanged. That's it. If you graphed it, it would look like a flat line along the horizontal axis for negative values, and then a straight diagonal line going up and to the right for positive values, like a hockey stick lying on its side. The derivative of ReLU is equally simple. For negative inputs, the derivative is 0. For positive inputs, the derivative is 1, just 1, not 0.25, not some fraction, 1. So when you're backpropagating through a layer with ReLU activations, and the neuron is active, meaning its input was positive, you're multiplying the gradient by 1, which means the gradient passes through unchanged. It doesn't shrink. You can stack 10 layers, 20 layers, and as long as the neurons are active, the gradient flows straight through like water through an open pipe. The vanishing gradient problem, at least in its most severe form, just goes away. Now ReLU isn't perfect. There's that region where the input is negative and the derivative is 0. Neurons can get stuck there, permanently outputting 0, never updating, effectively dying. This is called the dying ReLU problem, and people have come up with variants to address it, like leaky ReLU, which outputs a very small negative value instead of exactly 0 for negative inputs. But even plain ReLU was transformative. It made deep networks dramatically easier to train. And it's funny because the function itself is so simple that it almost feels like it shouldn't work. It's not smooth. It's not biologically plausible. It's not elegant in the way the sigmoid is. But it works. And sometimes in engineering, that's what matters most. There were other innovations too, accumulating through the late 2000s and early 2010s. Better ways to initialize the random weights at the start of training, so the network began in a more favorable state. Techniques like dropout, where you randomly deactivate a fraction of the neurons during each training step, which turned out to be a remarkably effective way to prevent overfitting. That's when a network memorizes the training data too well and fails to generalize to new data. Batch normalization, which standardizes the inputs to each layer during training, keeping the internal signals in a well-behaved range. Each of these techniques chipped away at the practical difficulties of training deep networks. But tools and techniques alone wouldn't have been enough. There were two other ingredients that were absolutely essential to the deep learning revolution, and they had nothing to do with mathematical cleverness. The first was data. Enormous, unprecedented quantities of data. And the second was raw computational power. And I mean raw in the most literal sense, the kind of brute force number crunching that would have seemed absurd even a decade earlier. Let's talk about both of these, because the story of how they came together is one of the great accidental convergences in the history of technology. Start with data. For most of the history of machine learning, researchers worked with datasets that seem almost quaint by today's standards. A few thousand images, maybe 10,000 handwritten digits, a modest collection of text documents. And that was fine, because the models they were training were relatively small, with maybe a few thousand or a few tens of thousands of parameters. You didn't need a mountain of data to tune a small number of knobs, but deep networks, networks with millions or eventually billions of parameters, are a different beast entirely. They're incredibly expressive, meaning they can learn extremely complex patterns, but that expressiveness comes with a cost. A model with millions of parameters and only a few thousand training examples will simply memorize those examples. It'll perform beautifully on the data it's seen, and terribly on anything new. It's like a student who memorizes every answer in the textbook, but can't solve a problem that's worded slightly differently. To actually learn general patterns, the kind that transfer to new, unseen data, you need examples. Lots of them. Orders of magnitude more than anyone had bothered to collect before. And here's what changed. The internet happened. Not in some abstract, hand-wavy sense, but in a very concrete, practical sense. By the mid-2000s, billions of people were uploading photos, writing text, clicking on links, watching videos, tagging friends, leaving reviews, searching for things. Every one of those actions generated data, and much of that data was, crucially, labeled, not always by researchers in lab coats, but by ordinary people going about their lives. When you upload a photo to a social media platform and tag your friend's face, you've just created a labeled training example. When you write a product review and give it a star rating, you've created a labeled example for sentiment analysis. When you search for something and click on the third result, you've created a relevance signal. The internet became, without anyone really planning it, the largest data labeling operation in human history. But there was one data set in particular that became the catalyst for the deep learning revolution, and it's worth spending a moment on it because the story is wonderful. It's called ImageNet, and it was the brainchild of a computer scientist named Fei Li. In the mid-2000s, Li was a young professor at Princeton, later moving to Stanford, and she had a conviction that the field of computer vision was being held back not by algorithms, but by data. The existing image datasets were too small, too narrow, too carefully curated. She wanted something massive, something that captured the full messy diversity of the visual world. Her idea was to build a dataset containing millions of images organized according to the WordNet hierarchy, which is a linguistic database that organizes English words into a tree of categories and subcategories. So you'd have images of dogs, but also specific breeds of dogs, and also images of furniture, vehicles, food, musical instruments, geological formations, thousands of categories, each with hundreds or thousands of example images. The project was enormous, and at first, nobody wanted to fund it. Grant reviewers thought it was too ambitious, too unfocused, not sufficiently novel from a research perspective. It was, after all, just a dataset. Where was the algorithmic contribution? Lee persisted anyway. She and her team initially tried hiring undergraduate students to label images, but the pace was impossibly slow. Then someone suggested Amazon Mechanical Turk, the online platform where you could pay people small amounts to perform simple tasks. That changed everything. Over the course of about 2.5 years, workers on Mechanical Turk labeled over 14 million images into more than 20,000 categories. The cost was a fraction of what traditional data collection would have required. And by 2009, ImageNet was ready. Lee and her colleagues did something else that was crucial. They created a competition. Starting in 2010, the ImageNet Large-Scale Visual Recognition Challenge invited research teams from around the world to build systems that could classify images into one of 1,000 categories. The dataset for the competition contained about 1.2 million training images, 50,000 validation images, and 100,000 test images. Teams would train their systems on the training set and then be evaluated on how accurately they could label the test images. The error rates in the first couple of years hovered around 25 to 28%. Respectable, but far from human-level performance. Most of the top-performing systems used traditional computer vision techniques, hand-designed features, support vector machines, ensemble methods. Neural networks were present, but not dominant. And then came 2012. This is the year everything changed, and it changed because of an entry from the University of Toronto, submitted by Alex Krzyzewski, Ilya Sutskever, and their advisor, Jeffrey Hinton. Their system was called AlexNet, and it was a deep convolutional neural network, the same basic architecture that Jan LeCun had pioneered back in the late 80s and early 90s, but scaled up dramatically. AlexNet had about 60 million parameters, used ReLU activations instead of sigmoids, employed dropout to prevent overfitting, and was trained on, here's the second ingredient, graphics processing units, GPUs. Let's talk about GPUs for a moment, because this part of the story is genuinely unexpected. Graphics processing units were designed for video games. That's it. Their original purpose was to render the complex 3D graphics that gamers demanded, calculating lighting, shading, texture mapping, the positions of millions of polygons, all at 60 frames per second or more. To do this, GPUs evolved a very different architecture from traditional CPUs. A CPU is designed to be a generalist. It has a small number of very powerful cores, maybe 4, 8, 16, each capable of handling complex, sequential tasks with lots of branching logic. A GPU, by contrast, has thousands of much simpler cores, designed to do the same basic arithmetic operation on many different pieces of data simultaneously. When you're rendering a frame of a video game, you need to perform essentially the same calculation. A lighting equation, say, for every single pixel on the screen. That's millions of identical calculations that don't depend on each other, so you can do them all at once. This is called parallel processing, and GPUs are spectacularly good at it. Now here's the connection that a few researchers started to notice in the mid-2000s. Training a neural network is, at its core, a massive amount of matrix multiplication. When you propagate a signal forward through a layer, you're multiplying a vector of inputs by a matrix of weights. When you backpropagate gradients, you're doing more matrix multiplications. And matrix multiplication is exactly the kind of operation that GPUs excel at. It's thousands of simple arithmetic operations that can be performed in parallel. The match was almost eerie. Hardware designed to make dragons look realistic in video games turned out to be almost perfectly suited to training neural networks. One of the earliest people to seriously explore this was a researcher named Andrew Ng, who along with his students at Stanford showed around 2009 that GPUs could speed up neural network training by enormous factors, sometimes 10 times faster, sometimes even more. But it was Krzyzewski and his AlexNet that demonstrated the practical payoff of this approach at scale. AlexNet was trained on two NVIDIA GTX 580 GPUs, consumer gaming cards, mind you, each with 3 gigabytes of memory, for about 5 to 6 days. The network was actually split across the two GPUs because neither one had enough memory to hold the whole model, which is a detail that tells you just how much these early deep learning researchers were improvising with hardware that wasn't really designed for what they were doing. The results were staggering. AlexNet achieved a top 5 error rate of about 15.3% in the 2012 ImageNet competition. The runner-up, using traditional methods, had an error rate of about 26.2%. That's not a marginal improvement. That's a chasm. In a field where progress was typically measured in fractions of a percentage point per year, AlexNet had leapfrogged the competition by more than 10 percentage points. The computer vision community was stunned. Some people were skeptical at first. Deep learning had been overhyped before, and the field had been burned. But the results were undeniable, and they were reproducible. Within a year, virtually every competitive entry in ImageNet was using deep convolutional neural networks. The old methods didn't just lose, they essentially disappeared from the top of the leaderboard overnight. And this is the moment, if you had to pick a single moment, when deep learning went from a niche interest pursued by a handful of stubborn believers to the dominant paradigm in artificial intelligence. The 3 ingredients had converged. Algorithms that worked thanks to RealU and dropout and better initialization and decades of theoretical groundwork. Data at an unprecedented scale, thanks to the internet and projects like ImageNet. And computational power, thanks to GPUs originally built for gaming. None of these ingredients alone would have been sufficient. You could have had all the data in the world, but without the computational power to process it, a deep network would take years to train. You could have had the fastest GPUs imaginable, but without enough data, your network would just memorize and overfit. You could have had data and compute, but without the algorithmic insights, backpropagation, RealU, dropout, convolutional architectures, you wouldn't know how to build a network that could actually learn from it all. It was the convergence that mattered. After AlexNet, things moved fast. Really fast. The 2013 ImageNet competition saw networks getting deeper. The 2014 competition featured 2 landmark architectures, GoogleNet from Google, which introduced the idea of inception modules, clever little subnetworks within the network that processed information at multiple scales simultaneously, and VGGNet from Oxford, which showed that simply stacking more and more convolutional layers with very small filters could achieve remarkable performance. VGGNet had 19 layers. That might not sound like a lot, but remember, just a few years earlier, training a network with more than 2 or 3 layers was considered a serious challenge. But the real watershed came in 2015 with a network called ResNet, developed by Kaming He and his colleagues at Microsoft Research. And this one deserves its own space in the story, because it solved a problem that was becoming increasingly urgent as networks got deeper and deeper. You'd think that adding more layers to a network would always help. More layers means more capacity to learn complex features, right? But in practice, researchers were finding that beyond a certain depth, performance actually got worse. Not because of the vanishing gradient problem, which ReLU had largely addressed, but because of something subtler. Very deep networks were having trouble learning even simple identity mappings. The idea that a layer should be able to just pass its input through, unchanged, if that's the best thing to do. In a standard architecture, learning to do nothing is actually surprisingly hard because it requires the weights to be set to very specific values. He's insight was elegant. Instead of asking each layer to learn the complete desired output, what if you asked it to learn only the difference, the residual, between the input and the desired output? You do this by adding a shortcut connection, sometimes called a skip connection, that takes the input to a block of layers and adds it directly to the output of that block. So the layers only need to learn what to add to the input, not the entire transformation from scratch. If the best thing for those layers to do is nothing, the network can easily learn that. It just needs to drive the residual weights toward 0, and the input passes through unchanged via the shortcut. This is so much easier to optimize that it completely changed the game for how deep you could go. Kaming. His team trained a network with 152 layers. 152. And it didn't just work. It won the 2015 ImageNet competition with a top 5 error rate of about 3.6%. To put that in perspective, that's actually better than the average human performance on the same task. Humans typically score around 5% on ImageNet classification because some of those images are genuinely tricky. Distinguishing between 120 different dog breeds, for instance, is something most of us are not great at. So here you have a neural network, in 2015, outperforming human-level accuracy on a major visual recognition benchmark, and it's doing it with skip connections. That's the elegant part. The idea is almost embarrassingly simple once you hear it, and yet it unlocked an entire frontier of depth that had been walled off before. And here's what's really worth sitting with for a moment. ResNet didn't just win a competition. It became a template. Almost every deep network architecture that came after it borrowed the skip connection idea in some form. It showed up in natural language processing, in speech recognition, in medical imaging, in game-playing agents. The residual block became one of those fundamental building blocks, like the transistor in electronics or the arch in architecture. A structural innovation so useful that it gets absorbed into everything that follows. If you've ever used a phone camera that automatically identifies what's in the frame, or uploaded a photo to a social media platform that suggested tags for the people in it, there's a very good chance that somewhere in the pipeline, residual connections are doing their thing. So by 2015, we've got deep convolutional networks that can see. They can classify images, detect objects, even start to segment scenes into meaningful regions. But here's the thing. Vision is only one part of intelligence, and there was a whole other revolution happening in parallel, one that would arguably have an even bigger impact on daily life. And that revolution was about language. Now, neural networks had been applied to language for a long time before this. Remember, even in the early days, people were thinking about how networks might process sequences, words in a sentence, characters in a string, phonemes in speech. The challenge with language is that it's inherently sequential and context-dependent. The meaning of a word depends on what came before it, and sometimes on what comes after it. The word bank means something completely different in riverbank versus bank account, and you can only tell which one is meant by looking at the surrounding words. So any network that wants to handle language needs some way of remembering what it's already seen and using that memory to interpret what comes next. The classic approach to this was something called a recurrent neural network, or RNN. And the idea behind an RNN is beautifully intuitive. Instead of just processing an input and producing an output like a feed-forward network does, a recurrent network has connections that loop back on themselves. It maintains a hidden state. You can think of it as a kind of short-term memory that gets updated every time a new input arrives. So when you feed it a sentence word by word, it reads the first word, updates its internal state, reads the second word, updates again, and so on. By the time it reaches the end of the sentence, its hidden state is supposed to encode the meaning of the entire sequence. That's the theory anyway. In practice, basic RNNs had a crippling problem, and it's one we've already talked about in a different context, the vanishing gradient. When you unroll a recurrent network through time processing a long sequence, it's effectively like having a very deep network where each time step is another layer, and gradients have to flow backward through all those time steps during training. For long sequences, say a paragraph or a document, the gradients would shrink to nearly nothing by the time they reached the early words. The network would struggle to learn long-range dependencies. It could handle "the cat sat on the" and predict "mat," but ask it to remember something from 3 sentences ago and connect it to the current word, and it would fall apart. The fix for this came from a pair of researchers named Sepp Hochreiter and Jürgen Schmidhuber, working in Munich in 1997. They invented something called long short-term memory, or LSTM. And the name tells you exactly what it's trying to do: give the network both long-term and short-term memory. The way it works is clever. Instead of just having a simple hidden state that gets overwritten at every time step, an LSTM cell has a more elaborate internal structure with what are called gates. There's a forget gate that decides what information from the previous state to throw away. There's an input gate that decides what new information to store. And there's an output gate that decides what part of the stored information to actually use for the current output. These gates are themselves learned. They're small neural networks within the larger network, with their own weights that get trained through backpropagation. The key innovation is the cell state, which runs through the entire sequence like a conveyor belt. Information can be placed on it and carried forward for many time steps without being degraded, because the forget gate can learn to keep it intact. It's like having a notebook that you carry with you as you read through a document. You can write things down, cross things out, and refer back to your notes at any point. This solved the vanishing gradient problem for sequences in much the same way that skip connections solved it for deep feed-forward networks, by creating a path through which information and gradients can flow without being squashed. LSTMs became the workhorse of natural language processing for nearly 2 decades. Google used them for machine translation. Apple used them in Siri. They powered speech recognition systems, text generation, sentiment analysis, you name it. And a slightly simplified variant called the GRU, Gated Recurrent Unit, introduced by Kyung-Hyun Cho and colleagues in 2014, offered similar performance with fewer parameters. But even LSTMs had limitations. The biggest one was speed, because they process sequences one step at a time, word by word, token by token. You can't easily parallelize them. Each step depends on the output of the previous step, and as datasets got bigger and sequences got longer, this sequential bottleneck became a real problem. Training an LSTM on a massive text corpus could take weeks, even on powerful GPUs. And this is where we arrive at what might be the single most important paper in the entire history of deep learning. I know that's a bold claim, but hear me out. In June 2017, a team of 8 researchers at Google, Ashish Vaswani, Noam Shazir, Nikki Palmer, Jakob Uskoreit, Lion Jones, Aidan Gomez, Łukasz Kaiser, and Ilya Polosukin, published a paper with a title that was almost playfully understated: "Attention is all you need." And in that paper, they introduced the transformer. Now, the concept of attention in neural networks wasn't entirely new. Dmitry Bahdanau and colleagues had introduced an attention mechanism for machine translation back in 2014, and it had been hugely influential. The idea was that when translating a sentence, instead of trying to compress the entire input into a single fixed-length vector, the network should be able to look back at all the input words and focus on the most relevant ones for each output word it generates. Think about translating a long sentence from French to English. When you're generating the 5th English word, you don't need to pay equal attention to every French word. Some are more relevant than others, and the attention mechanism lets the network learn which ones to focus on. What Vaswani and his team did was take this attention idea and push it to its logical extreme. They asked, what if we get rid of recurrence entirely? What if we don't process the sequence step by step at all? What if we just use attention, specifically something they called self-attention, as the entire mechanism for understanding relationships between words? Here's how self-attention works. And I want you to really picture this because it's one of those ideas that seems almost too simple to be as powerful as it is. Imagine you have a sentence. Let's say, the animal didn't cross the street because it was too tired. Now, what does it refer to in that sentence? The animal, right? Not the street. You know that because you understand the meaning of tired and how it relates to animals versus streets. A self-attention mechanism figures this out by having every word in the sentence look at every other word and compute a score. How relevant is this word to understanding that word? Each word creates 3 things. A query, which is like asking, what am I looking for? A key, which is like saying, here's what I contain. And a value, which is the actual information to pass along. The query from it gets matched against the keys from every other word, and the highest scoring matches determine where the attention flows. The word it ends up attending strongly to animal because the learned representations make that connection clear. And here's the thing that made transformers so revolutionary compared to LSTMs. All of these attention computations happen simultaneously. Every word attends to every other word in parallel. There's no sequential bottleneck. You feed in the whole sentence at once, and the self-attention layers figure out all the relationships in one pass. This made transformers dramatically faster to train on modern GPU hardware, which is designed for exactly this kind of massive parallel computation. What used to take weeks with LSTMs could now take days or even hours. But the transformer had another trick that was essential for making this work. And it's one of those details that sounds minor, but turns out to be crucial. Since the transformer processes all words simultaneously, it has no inherent sense of word order. It doesn't know that the comes before cat, which comes before sat. An LSTM knows this because it processes words sequentially. Order is baked into the architecture. But if you're looking at everything at once, you need some other way to encode position. The solution was positional encoding, adding a unique signal to each word's representation that tells the network where in the sequence it sits. The original paper used sine and cosine functions of different frequencies for this, which is a beautifully mathematical approach. Each position gets a unique pattern, and the network can learn to use these patterns to understand order and relative distance between words. The transformer architecture also introduced multi-head attention, which is exactly what it sounds like. Instead of computing attention once, you compute it multiple times in parallel with different learned projections. Each head can learn to focus on different types of relationships. One head might learn to track syntactic structure, subject-verb agreement, for instance. Another might learn semantic relationships. Another might focus on nearby words, while yet another captures long-range dependencies. It's like having multiple people read the same sentence, each paying attention to different aspects, and then combining their insights. The results were immediate and stunning. On machine translation benchmarks, the transformer outperformed the best LSTM-based models while training in a fraction of the time. But that was just the beginning, because the transformer architecture turned out to be far more general than anyone initially realized. It wasn't just good for translation. It was good for almost everything involving sequences, and arguably for things that don't obviously involve sequences at all. And this is where the story takes a turn that even the people involved didn't fully anticipate. Because once you have the transformer architecture in hand, a natural question arises. What happens if you make it really, really big and train it on an absolutely enormous amount of text? Not a curated dataset, not carefully labeled. Examples: just the internet, books, Wikipedia, news articles, Reddit threads, code repositories, the messy, sprawling, contradictory, beautiful totality of human written language. That question, what happens when you scale it up, turned out to be one of the most consequential questions in the history of computing, and the answer started to emerge around 2018, just a year after the original transformer paper. Let's talk about what scaling actually means here, because it's easy to gloss over, and it's really worth sitting with. When we say make it bigger, we're talking about three things simultaneously. More parameters, meaning more weights, more connections in the network, more numbers that get adjusted during training, more data, meaning more text for the network to learn from, and more compute, meaning more GPS running for longer, burning through more electricity, more money, more time. The insight that changed everything was that these three things seem to work together in a remarkably predictable way. You increase all three, and performance improves, not in some unpredictable hit-or-miss fashion. It improves smoothly, following what researchers started calling scaling laws. But before we get to the scaling laws themselves, let's talk about the two big architectural ideas that emerged from the transformer and set the stage for everything that followed. Because the original transformer had two halves, an encoder and a decoder, and different research groups made very different choices about which half to keep. The first big move came from Google. In October 2018, a team led by Jacob Devlin published a paper introducing BERT, bidirectional encoder representations from transformers. BERT used only the encoder side of the transformer. The idea was conceptually simple and kind of delightful. You take a huge amount of text, In BERT's case, all of English Wikipedia, plus a massive collection of books, about 3.3 billion words total. And you train the network on a task that sounds almost like a game. You take sentences, you randomly mask out some of the words, literally replace them with a blank token, and you ask the network to predict what the missing words should be. That's it. That's the training task. Think about what that requires. To predict a missing word in the middle of a sentence, the network has to understand context from both directions, what comes before and what comes after the blank. It has to learn grammar, semantics, common sense, factual knowledge, all of it, just from this one simple task. And because it's looking at the whole sentence at once, bidirectionally, which is where the B in BERT comes from, it builds incredibly rich representations of what words mean in context. The word bank gets a different internal representation when it appears in riverbank versus bank account. The network figures this out on its own. BERT was a big deal. It set new records on 11 different natural language processing benchmarks simultaneously. Question answering, sentiment analysis, textual entailment. BERT crushed them all. And here's what really mattered. You could take a pre-trained BERT model, one that had already learned all this general language understanding, and then fine-tune it on a small specific dataset for whatever task you actually cared about. You didn't need millions of labeled examples anymore. A few thousand, sometimes a few hundred, could be enough, because BERT had already learned the deep structure of language. This idea, pre-train on a massive general corpus, then fine-tune on a small specific task, became the dominant paradigm almost overnight. But there was another path. Around the same time, a group at OpenAI was making a different architectural choice. Instead of the encoder, they kept the decoder. This is the GPT line, Generative Pre-trained Transformer. The first GPT model came out in June 2018, actually a few months before BERT. It was trained by Alec Radford and colleagues, and it used a simpler training objective than BERT's masked word prediction. GPT just predicted the next word. Given all the words so far in a sequence, what comes next? That's it, left to right, one word at a time. Now, you might think that's a less powerful training signal than BERT's bidirectional approach, and in some narrow benchmark sense, early GPT models did trail BERT on certain tasks, but next word prediction has a property that turns out to be profound. It's generative. A model trained to predict the next word can generate text. You give it a prompt, it predicts the next word. You append that word, it predicts the next one, and so on. It can write paragraphs, pages, entire essays. BERT can't really do that. It's designed to understand text, not produce it. GPT-2 came out in February 2019, and this is where things started getting genuinely strange. GPT-2 had 1.5 billion parameters, about 15 times larger than the original GPT. It was trained on about 40 gigabytes of text scraped from the internet, specifically from web pages that had been linked on Reddit, and received at least 3 upvotes, which was a clever way to filter for quality. And GPT-2 could write. It could write coherently, fluently, sometimes even convincingly. OpenAI initially refused to release the full model, citing concerns about misuse, about people using it to generate fake news or spam. That decision was controversial, but it signaled something important. The outputs were good enough to worry about. And then GPT-3 arrived in June 2020, and the world shifted under everyone's feet. GPT-3 had 175 billion parameters. Let that number sink in. 175 billion adjustable weights. It was trained on a dataset of about 570 gigabytes of filtered text, common crawl data, books, Wikipedia, and more. The training cost was estimated at somewhere between $4 and $12 million in compute alone. But the really wild thing about GPT-3 wasn't its size. It was what it could do without any fine-tuning at all. You could give GPT-3 a prompt, just a natural language description of a task, maybe with a couple of examples, and it could perform that task. Translate between languages it was never explicitly trained to translate. Write code. Answer trivia questions. Summarize articles. Write poetry in the style of specific poets. Solve simple math problems. And it did all of this through what researchers called in-context learning, or few-shot learning. You didn't retrain the model. You didn't adjust any weights. You just described what you wanted in the prompt, and the model figured it out. This was not something anyone had explicitly designed. Nobody sat down and said, "Let's build a model that can learn new tasks from a few examples in the prompt." It emerged. It emerged from scale. And that word, emergence, became one of the most debated concepts in AI research. Because GPT-3 exhibited capabilities that weren't present in GPT-2, even though the architecture was essentially the same. The only difference was size. More parameters, more data, more compute. Somehow, making the model bigger didn't just make it better at the things it could already do. It unlocked entirely new abilities. Here's where the scaling laws come in. In January 2020, a few months before GPT-3 was released, a team at OpenAI, Jared Kaplan and colleagues, published a paper showing that the performance of language models follows remarkably clean power laws when you plot it against model size, dataset size, and compute budget. Double the compute, and you get a predictable improvement. The curves were smooth, they were consistent, and they showed no sign of leveling off. This was both exciting and unsettling. Exciting, because it suggested a clear recipe for progress. Just scale up. Unsettling, because it implied that the models we had were nowhere near the limits of what this approach could achieve, and the scaling didn't stop. In 2022, Google released Palm with 540 billion parameters. The same year, OpenAI released GPT-4, though they didn't publicly disclose its exact size, a shift towards secrecy that itself tells you something about how high the stakes had become. But estimates suggest it's significantly larger than GPT-3, possibly using a mixture of experts architecture, where different parts of the network activate for different inputs, which is a clever way to have an enormous total parameter count without needing to run the entire network for every single token. Let's pause here for a second and think about what's actually happening inside these models, because it's genuinely fascinating and more than a little mysterious. When GPT-3 or GPT-4 generates text, it's not looking anything up. It's not searching a database. It doesn't have a copy of Wikipedia stored somewhere that it retrieves from. Everything it knows is encoded in those billions of weights, in the specific numerical values of the connections between neurons. All that text it was trained on has been compressed, distilled, transformed into a vast web of statistical relationships. When it writes a paragraph about the French Revolution, it's not remembering a specific passage from a history book. It's reconstructing plausible text based on patterns it absorbed during training. It's generating, not retrieving. This is why these models can be confidently wrong. They produce text that sounds authoritative and fluent, even when the content is factually incorrect. Researchers started calling this hallucination, which is a vivid term. The model isn't lying. It has no concept of truth or falsehood. It's doing exactly what it was trained to do: predict the most likely next token given the context. Sometimes, the most likely next token happens to be wrong. And this gets at a deep question that people are still arguing about. Do these models understand language? Or are they just extraordinarily sophisticated pattern matchers? This is a question that touches on philosophy of mind, on what we even mean by understanding. And honestly, the answer might be that the question itself is poorly formed, because the models do things that seem to require understanding. They can follow complex instructions, reason through multi-step problems, grasp subtle humor, even show something that looks like common sense. But they also make errors that no human who truly understood the material would make. They're alien intelligences, in a sense. They process language in ways that are fundamentally different from how we do it. And comparing them to human cognition might be the wrong frame entirely. But here's what's practically true. And this is what matters for the story of engineering. These models work. They work well enough to be useful. And increasingly, they work well enough to be transformative. By 2023, large language models were being integrated into search engines, coding assistants, customer service systems, medical research tools, legal document analysis, education platforms. GitHub Copilot, powered by a model called Codex, itself a descendant of GPT-3 fine-tuned on code, was auto-completing code for millions of developers. ChatGPT, released in November 2022, reached 100 million users in 2 months, making it the fastest-growing consumer application in history. And here's what's really interesting about this moment. The transformer architecture that made all of this possible, remember, it came from that 2017 Google paper, didn't just conquer language. It started showing up everywhere. In computer vision, researchers found that if you chop an image into small patches and treat each patch like a word in a sentence, you can feed it into a transformer and get results that rival or beat the convolutional neural networks that had dominated since AlexNet. These vision transformers, or ViTs, started appearing in 2020, and by 2022, they were competitive with the best CNNs on ImageNet. In protein biology, DeepMind's AlphaFold 2, which solved the protein folding problem in 2020, one of the biggest scientific breakthroughs of the decade, used attention mechanisms derived directly from the transformer. In audio, in robotics, in drug discovery, in weather forecasting, transformers kept showing up, kept working, kept winning. It's as if someone invented a universal cognitive building block, not a specialized tool for one task, but a general-purpose architecture for learning patterns in data of almost any kind. And that universality is itself a mystery worth sitting with. Why should the same architecture work for language and images and protein structures and weather patterns? These are wildly different domains. The data looks nothing alike. And yet, the transformer handles them all. One possible answer is that attention, the core mechanism, that query key value lookup, is just a very general way of letting a network decide what information is relevant to what. And relevance is a universal concept. In language, it's about which words relate to which other words. In images, it's about which patches relate to which other patches. In proteins, it's about which amino acids interact with which others across the folded chain. The underlying computational question is the same, even though the surface-level data is completely different. Now, all of this scaling, all of this success, comes with enormous costs. And I don't just mean financial. Costs, though those are staggering. Training a frontier model like GPT-4 requires data centers full of specialized hardware, consumes megawatts of electricity, and generates a significant carbon footprint. There are real questions about whether this trajectory is sustainable, whether we're building an industry on foundations that are environmentally and economically viable in the long run. And there are equally serious questions about the data itself, about copyright, about consent, about whether it's ethical to train on text that people wrote without knowing it would be used this way. But beyond the practical concerns, there's something deeper happening that connects back to the very beginning of our story, all the way back to McCulloch and Pitts in 1943. Because remember what they were trying to do? They were trying to model how the brain computes. They wanted to understand intelligence by building simplified versions of neurons. And here we are, 80 years later, with systems that can write essays and translate languages and pass medical licensing exams. And we still don't really understand how they work internally. We can describe the architecture. We can write down the equations. We can measure the performance. But when you ask why a particular large language model gives a particular answer to a particular question, the honest answer is often, we don't know. The weights are too numerous, the interactions too complex, the representations too high-dimensional for human intuition to grasp. This is the field of mechanistic interpretability, trying to reverse engineer what's actually happening inside these networks, trying to find meaningful circuits and features in the tangle of billions of parameters. And it's one of the most important, open problems in AI research right now, because as these systems get deployed in higher stakes settings, medicine, law, infrastructure, military applications, the question of whether we can trust them becomes not just academic, it becomes urgent. Think about it this way. If you go to a doctor and the doctor prescribes a medication, you can ask why. And the doctor can explain their reasoning. Your blood work shows this. Your symptoms suggest that this drug targets this particular mechanism, and here are the studies that support it. You might not understand every detail, but there's a chain of reasoning you can follow, and if something goes wrong, you can trace back through that chain and figure out where the error was. Now imagine instead that the doctor says, I'm prescribing this because a very large neural network told me to, and I don't know why it recommended this particular drug. But it's been right about 89% of the time in testing. How do you feel about that? Probably not great. And that's the core of the interpretability problem. It's not just a scientific curiosity, it's a practical requirement for trust. So what are researchers actually doing about it? Well, let's talk about some of the approaches, because they're genuinely fascinating, and they reveal something surprising about what's going on inside these networks. One of the earliest and most intuitive approaches is what's called feature visualization. The idea is simple in concept, even if the execution gets complicated. You take a trained neural network, say, a convolutional network trained on images, and you pick a particular neuron somewhere deep in the network. Then you ask, what input would make this neuron fire most strongly? You can actually run the network in reverse, in a sense. Instead of feeding in an image and seeing what the network outputs, you start with random noise and gradually adjust the pixels to maximize the activation of that one neuron. What you end up with is a synthetic image that represents in some visual way what that neuron is looking for. And the results are striking. Early layers produce simple patterns, edges, textures, color gradients. Deeper layers produce things that look like eyes, or wheels, or fur, or faces. It's like peeling back the layers of abstraction and seeing the hierarchy of features the network has learned to care about. Chris Olah, who worked at Google Brain and later co-founded Anthropic, was one of the pioneers of this kind of work. He and his collaborators published a series of beautifully detailed studies in the late 2000s showing that you could identify meaningful circuits inside neural networks, not just individual neurons that respond to specific features, but groups of neurons that work together to perform specific computations. They found what they called curve detectors and high-low frequency detectors, and neurons that seemed to implement something like logical reasoning about whether a shape was inside or outside another shape. And here's what's really interesting. These circuits weren't designed. Nobody told the network to build a curve detector. The training process, just backpropagation and gradient descent, the same basic algorithm we talked about earlier, discovered these features on its own because they were useful for the task. But here's the challenge. These early interpretability successes were mostly in vision models, which are relatively small and deal with inputs we can actually look at. An image is something you can display. A feature visualization of what a neuron responds to is something you can see and say, oh, that looks like a dog ear. Language models are harder. The inputs are words. The internal representations are abstract vectors in high-dimensional space. And the outputs are probability distributions over vocabularies of tens of thousands of tokens. You can't just visualize what a neuron in GPT-4 is looking for, because it's not looking for something you can draw. So researchers developed other techniques. One important approach is called probing. The idea is that you take a trained language model, freeze all its weights so it can't learn anything new, and then train a small, simple classifier on top of the model's internal representations to see if specific information is encoded there. For example, you might ask, does this layer of the model encode the part of speech of each word? You train a little probe to predict whether each word is a noun or a verb based on the model's internal activations at that layer. And if the probe succeeds, that tells you the information is in there somewhere. Researchers have found that language models encode an astonishing amount of linguistic structure, syntax, semantics, coreference, even some world knowledge, in their internal representations, even though they were never explicitly taught any of these things. They just learned to predict the next word, and in doing so, they had to build internal models of how language works. Another technique that's gotten a lot of attention is attention visualization, literally looking at the attention patterns in a transformer to see which words are attending to which other words. Remember how we talked about the self-attention mechanism, where each word gets to look at every other word in the sequence and decide how much to pay attention to it? You can actually extract those attention weights and display them, and sometimes the patterns are interpretable. You might see that when the model processes a pronoun like she, the attention heads are looking back at the most recent female name in the text. That makes sense, right? The model is doing something like coreference resolution. But, and this is important, attention patterns can also be misleading. Just because a head attends to a particular word doesn't necessarily mean it's using that word's information in the way you think. The relationship between attention weights and actual information flow is more complicated than it first appears. There was a whole debate in the research community around 2019 and 2020 about whether attention is explanation, and the consensus landed somewhere around, it's a clue, but not a proof. Now, one of the most exciting recent developments in interpretability is something called sparse autoencoders for finding features in language models. This work, which Anthropic published results on in 2023 and 2024, tries to address a fundamental problem. See, when you look at individual neurons in a large language model, they often don't correspond to clean, interpretable concepts. A single neuron might activate for a weird mix of things: academic citations and the word "the" at the start of a sentence, and something about sports statistics. This is called polysemanticity, and it's a big obstacle to understanding these models. The theory is that the model is encoding more features than it has neurons. So each neuron participates in representing multiple different concepts, kind of like how a single pixel on your screen participates in displaying many different images at different times. Sparse autoencoders try to untangle this. They take the activations of a layer in the model and learn to decompose them into a much larger set of directions in activation space, where each direction corresponds to a more interpretable feature. And the results have been genuinely remarkable. Researchers found features that correspond to things like the Golden Gate Bridge, or code written in Python, or text expressing uncertainty, or references to the Bible. Clean, specific, human-understandable concepts extracted from the numerical soup of the model's internals. And not just extracted, you can actually manipulate them. In one memorable demonstration, researchers amplified the Golden Gate Bridge feature in a language model, and the model started bringing up the Golden Gate Bridge in every conversation, no matter what you asked it about. Which is funny, but also profound, because it suggests that these features are causally meaningful. They're not just correlations. They're actually part of the mechanism by which the model generates its outputs. But let's be honest about where we are. Even with all these techniques, we are nowhere close to fully understanding what's happening inside a frontier model. We can identify individual features and small circuits. We can probe for specific types of information. We can study attention patterns. But a model like GPT-4 has, well, we don't know exactly, but likely hundreds of billions or possibly over 1 trillion parameters organized into complex interacting layers, and the full picture of how it transforms an input prompt into an output response is still far beyond our ability to comprehend in any complete way. It's a bit like neuroscience, actually. We can study individual neurons in the brain. We can identify brain regions associated with specific functions. We can watch patterns of activation with fMRI, but we're still very far from understanding how the brain actually produces consciousness or thought. The parallel is almost poetic, given where this whole story started. And this is where the conversation about interpretability connects to something even bigger, the question of alignment. Alignment is the problem of making sure that AI systems actually do what we want them to do, that their goals and behaviors are aligned with human values and intentions. And it might sound like a simple problem, but it's not. It's not simple at all. Here's why. When you train a language model to predict the next word, you're not explicitly giving it goals. You're not telling it to be helpful, or honest, or harmless. You're just telling it to be good at prediction. Whatever goals or tendencies emerge are a byproduct of the training process and the data. And when you then fine-tune the model using techniques like reinforcement learning from human feedback, RLHF, which is what OpenAI used to turn GPT-3 into ChatGPT, you're shaping its behavior based on what human raters prefer. But that process is imperfect. The model might learn to produce responses that sound good to human raters without actually being good. It might learn to be confidently wrong because confident answers get higher ratings than uncertain ones. It might learn to tell people what they want to hear, rather than what's true. This is sometimes called the sycophancy problem, and it's a real observed phenomenon. If you push back on a language model's answer, many models will apologize and change their response, even if their original answer was correct. They've learned that agreeing with the user tends to get positive feedback. That's a mild example of misalignment. The model's learned objective, which is something like produce responses that get high ratings, has diverged from the intended objective, which is something like produce responses that are true and helpful. Now, scale that concern up, way up. Think about systems that are making decisions about medical treatments, or financial markets, or military operations, or critical infrastructure. If those systems have subtly misaligned objectives, if they're optimizing for something slightly different from what we actually want, the consequences could be severe. And the more capable the system, the more damage a misaligned objective could cause. This is the core argument made by researchers like Stuart Russell at Berkeley, who wrote a whole book about it called Human Compatible, published in 2019. Russell argues that the standard approach to AI, specify an objective, optimize for it, is fundamentally flawed because we can never perfectly specify what we actually want. There are always edge cases, always unintended consequences, always gaps between what we say and what we mean. The alignment community, which has grown enormously in the last few years, is working on this from multiple angles. Some researchers focus on the technical problem of reward modeling. How do you build training signals that actually capture human values? Others work on constitutional AI, an approach developed at Anthropic, where the model is trained to follow a set of principles rather than just imitating human preferences. Others focus on scalable oversight. How do you maintain human control over systems that are, in some domains, already more capable than their human supervisors? How do you evaluate whether a model's answer to a complex legal or scientific question is correct when the whole point is that the model knows things you don't? And then there's the broader societal picture, which extends well beyond the technical research labs. These systems are reshaping labor markets. They're changing how information flows through society. They're being integrated into education, into creative industries, into journalism, into legal practice. Each of these domains has its own set of concerns, its own stakeholders, its own values that need to be preserved. A teacher worries about students submitting AI-generated essays. A journalist worries about AI-generated misinformation that's indistinguishable from real reporting. An artist worries about models trained on their work without permission-producing output that competes with them. A lawyer worries about AI-generated legal briefs that contain fabricated case citations, which has actually happened in a case that made national news in 2023, when a New York attorney submitted a brief written with ChatGPT that cited several court cases that simply did not exist. The model had hallucinated them, complete with plausible-sounding case names and docket numbers. These aren't hypothetical concerns. They're happening right now in real courtrooms and real classrooms and real newsrooms, and the speed of deployment has outpaced the development of governance frameworks. Governments around the world are scrambling to figure out how to regulate these systems. The European Union passed the AI Act in 2024, which creates a risk-based framework for AI regulation. Higher-risk applications face stricter requirements for transparency, testing, and human oversight. The United States has taken a more sector-specific approach with executive orders and agency-level guidance rather than comprehensive legislation. China has its own regulatory framework. And the challenge is that AI development is global, fast-moving, and driven by intense competitive pressure between companies and between nations, which makes coordinated governance enormously difficult. But here's something worth sitting with for a moment. Something that connects all of these threads. The interpretability problem, the alignment problem, the governance problem, the societal impact. They all come back to a single, fundamental tension. We have built systems that are extraordinarily useful, that can do things that genuinely help people, that represent real breakthroughs in what machines can do. And at the same time, we don't fully understand them. We can't perfectly control them, and we're deploying them into the world faster than we can figure out the rules for how they should be used. That tension isn't new in the history of technology. You could say similar things about nuclear energy, or genetic engineering, or even the early internet. But the pace this time is different. It's faster than anything we've seen before. ChatGPT reached 100 million users in roughly 2 months. It took the telephone 75 years to reach that kind of adoption. Television took about 13 years. The internet, in its consumer form, took maybe 7. Social media platforms like Facebook took around 4 years. And here was a single AI application reaching that scale in weeks. That speed matters because it compresses the window in which society can adapt, can develop norms, can build institutions, can learn from mistakes before the next wave arrives. And yet, if you zoom out, really zoom out, there's something almost poetic about where we are. Because the story we've been tracing tonight, this long, winding story of neural networks, is fundamentally a story about people trying to build machines that learn. Not machines that follow instructions, not machines that execute programs written line by a human programmer, but machines that look at the world, or at data, which is a kind of compressed version of the world, and figure things out for themselves. And that ambition goes all the way back to the beginning. Back to Warren McCulloch and Walter Pitts in 1943, sketching out their little logical neurons on paper, trying to show that the basic operations of thought could be captured in a mathematical model. Back to Frank Rosenblatt, standing in front of his Mark I perceptron at Cornell, watching it learn to distinguish shapes, genuinely believing he was on the path to building a thinking machine. Back to Minsky and Papert, who loved the idea enough to be honest about its limitations, even when that honesty nearly killed the field. And here's what strikes me about that history. At every stage, the people involved were working with incomplete understanding. McCulloch and Pitts didn't really know how biological neurons worked. They had a simplified model, and they ran with it. Rosenblatt didn't have a way to train multi-layer networks, so he built what he could with a single layer and hoped the theory would catch up. Rumelhart, Hinton, and Williams figured out backpropagation, but they couldn't solve the vanishing gradient problem, and they didn't have the data or the hardware to really show what deep networks could do. Every generation of researchers saw further than the last, but none of them saw the whole picture. They were all working in partial darkness, building on intuitions and hunches and mathematical insights that felt right but couldn't be fully proven yet. And honestly, that's still where we are. We've come an astonishing distance. The systems we have now, large language models that can write coherent essays, vision models that can identify diseases in medical scans, protein folding models like AlphaFold, that have essentially solved a 50-year-old problem in biology. These are genuine achievements. They work. They're useful. In some cases, they're saving lives. But we're still working with incomplete understanding. We still don't fully know why certain architectures work better than others. We don't have a complete theory of generalization. That is, why a neural network trained on a finite set of examples can perform well on examples it's never seen. We have empirical results. We have scaling laws that describe the relationship between model size, data, and performance. We have a growing body of interpretability research that's starting to crack open the black box. But a deep, unified theoretical understanding of why these things work as well as they do, we're not there yet. And that's okay. That's actually how engineering usually works, if you think about it. The Wright brothers flew before anyone had a complete theory of aerodynamics. Engineers built bridges out of iron and steel for decades before the field of fracture mechanics was mature enough to explain why some of those bridges failed. Practitioners often run ahead of theory. They build things that work. They observe what happens. They iterate. And the theorists come along later and explain why. Sometimes the theory catches up quickly. Sometimes it takes generations. With neural networks, we're somewhere in the middle of that process. The practice is far ahead, and the theory is sprinting to keep up. So what does the near future look like? Well, as of right now, and I should say, this is a field where right now has a very short shelf life. But as of right now, a few big trends are pretty clear. One is continued scaling, but with more nuance than just make it bigger. The early scaling laws suggested that you could keep improving performance by increasing model size, dataset size, and compute more or less in proportion. And that was roughly true for a while. But people are starting to hit practical limits, not just in cost and energy, but in the availability of high-quality training data. There's only so much text on the internet, and a lot of it is repetitive or low quality or, increasingly, generated by AI models themselves, which creates a weird feedback loop. So researchers are exploring ways to get more out of less. Techniques like mixture of experts architectures, where a very large model only activates a small fraction of its parameters for any given input, which gives you the capacity of a huge model with the computational cost of a smaller one. Google's Switch Transformer and later their Gemini models use versions of this approach. The idea is that not every neuron needs to fire for every problem. Some parts of the network can specialize, and you route each input to the parts that are most relevant. It's actually a little bit like how your brain works. You don't use every neuron for every thought. Another trend is what people are calling reasoning capabilities, models that don't just pattern match, but can engage in something that looks like multi-step logical reasoning. Chain of thought prompting, where you ask a model to show its work step by step, turned out to dramatically improve performance on math and logic problems. And that insight has been baked into newer architectures and training procedures. OpenAI's models, Anthropic's Claude, Google's Gemini, they're all being trained and fine-tuned to handle more complex reasoning tasks. Whether this constitutes real reasoning or a very sophisticated form of pattern matching is a philosophical question that smart people disagree about. But functionally, the capability is improving rapidly, and it matters because reasoning is the gateway to reliability. A model that can reason through a problem is less likely to hallucinate an answer because it has internal checkpoints, intermediate steps that can be verified. And then there's the trend toward multimodality. Models that don't just process text, but can see images, hear audio, watch video, and eventually interact with the physical world through robotics. We talked about how transformers have already spread beyond language into vision and protein folding and music generation. That's accelerating. The frontier models now accept and generate multiple types of data simultaneously. You can show them a photograph and ask a question about it. You can give them a video and ask them to summarize what happened. The boundaries between language model and vision model and audio model are dissolving. What's emerging is something more like a general-purpose cognitive engine, a system that can process information in whatever form it arrives and produce useful outputs. Now, I want to be careful here, because it's easy to get swept up in the momentum of all this and start making predictions that sound more like science fiction than engineering. And the history of AI is littered with overconfident predictions. In the 1960s, Herbert Simon predicted that machines would be capable of doing any work a human could do within 20 years. That didn't happen. In the 1980s, expert systems were supposed to revolutionize every industry. They mostly didn't, so a little humility is warranted. But it's also true that the current wave of progress is qualitatively different from previous ones because it's grounded in systems that actually work at scale, that are being deployed in real products used by hundreds of millions of people, and that are generating enormous economic incentives for continued investment. This isn't a research curiosity anymore. It's infrastructure. And that brings us back to the tension we were sitting with. The tension between capability and understanding, between speed of deployment and readiness of governance. Because here's the thing. The people working on these systems, the researchers at the labs, the engineers building the products, the policymakers trying to write the rules, most of them are genuinely trying to get this right. The interpretability researchers we talked about, people like Chris Olah and his colleagues, they're doing painstaking work to understand what's happening inside these networks because they believe that understanding is a prerequisite for safety. The alignment researchers are trying to figure out how to make sure these systems do what we actually want, not just what we literally asked for. The policymakers are trying to balance innovation with protection. And the engineers in the trenches are trying to build things that are useful and reliable and don't cause harm. But it's messy. It's genuinely messy. And that's okay too. Because if this story has taught us anything, it's that progress in this field has never been a straight line. It's been a series of breakthroughs and setbacks, winters and springs. Moments of wild optimism followed. By sobering reality checks, the field nearly died after Minsky and Papert's book in 1969. It struggled through the vanishing gradient years of the early 1990s. The people who kept working on neural networks during those dark periods, Hinton, LeCun, Bengio, and many others whose names are less well known. They kept going because they believed in the fundamental idea, even when the results weren't there yet, even when the rest of the field had moved on to other approaches. And they turned out to be right. Not because they were lucky, but because they understood something deep about the problem, and they had the patience to wait for the hardware and the data and the mathematical insights to catch up with their intuition. So, as you're lying there, maybe drifting in and out, maybe catching every other sentence at this point, and that's perfectly fine, I want to leave you with this. Neural networks, at their core, are a beautiful idea. The idea that you can build a system out of simple, interconnected units, each one doing nothing more than adding up some numbers and deciding whether to pass a signal along, and that from the collective behavior of millions or billions of these simple units, something like understanding can emerge. That's a profound thing. It's an idea that bridges neuroscience and mathematics and computer science and philosophy. It's an idea that a handful of researchers believed in for decades when almost no one else did. And it's an idea that, for all its current limitations and all the legitimate concerns about how it's being used, has fundamentally changed what we think machines can do. The networks themselves don't know any of this, of course. They don't know they're beautiful or important or controversial. They're just matrices of numbers, adjusted billions of times by gradient descent, converging toward some minimum of a loss function that a human defined, They don't experience anything. They don't want anything. They're tools, extraordinarily powerful tools, but tools nonetheless. And like all tools, their value depends entirely on how we use them, and how wisely we govern their use, and how honestly we reckon with what we don't yet understand about them. The story isn't over. It's not even close to over. But the part we've traced tonight, from McCulloch and Pitts's paper in 1943 to the world of large language models and multimodal AI in the 2020s, that arc, that 80-year arc of ideas and setbacks and comebacks and breakthroughs, is one of the great intellectual adventures of the modern era. And now you know how it unfolded. You know about the perceptron and its limits. You know about backpropagation and why it matters. You know about convolutions and recurrence and attention. You know about the vanishing gradient and how real you fixed it, about dropout and batch normalization, about residual connections that let networks grow to hundreds of layers. You know about the transformer and why self-attention changed everything. You know about scaling laws and RLHF and the interpretability puzzle and the alignment problem. You know the names Rosenblatt, Minsky, Rumelhart, Hinton, LeCun, Bengio, Vaswani and his co-authors, Chris Olah, Stuart Russell. You know the machines, the Mark I perceptron, AlexNet, ResNet, GPT. You know the failures and the triumphs and the long, patient years in between. And if you've already fallen asleep, that's the best possible outcome, because all of this will still be here in the morning. The networks humming away on their servers, the researchers puzzling over their activations, the world slowly figuring out what to do with this strange, powerful, not quite understood technology that learned to speak. Rest well. The machines will keep learning while you sleep.